All right, so our next speaker is Shipra Agrawal. She's an assistant professor in the Department of Industrial Engineering and Operations Research at Columbia University. She received her PhD in computer science from Stanford University in 2011. And she's been at Microsoft Research before joining Columbia. She's done a lot of work in optimization, reinforcement learning, Bayesian modeling, decision-making under uncertainty. And let's see whether it works. Her talk is going to be on posterior sampling for reinforcement learning, if it shows up.
Is there a VGA?
Let's see.
Connecting to HDMI.
Okay.
How do I go to HDMI? Okay.
All set. Thanks.
Thank you. Thank you for inviting me here. It's oh, I need a mic. Yeah. Thank you for inviting me here. It's a really nice conference and really nice place. Today I'm going to shift gears a little bit and is it on? Hello? Yeah. All right. So I'm going to switch gears a little bit and talk about algorithms in reinforcement learning and model-based reinforcement learning. And the algorithm that I'll present is motivated by looking at reinforcement learning as a sequential decision-making problem. So think about a regular sequential decision-making problem where you have decisions to make in every round, but now the rewards that you get on making a decision depends not only just on the decision you make, but also on the state of the world where you make that decision. So you have a discrete rounds t is equals 1 to t, you observe the state and you take an action, and you observe a response in the form of reward as well as new state of the world. And again, because we don't know the model of the world in the sense of where the rewards, how the rewards are generated, how the states are transitioned, the challenge is to learn these models while making these decisions based on your observations, as well as at the same time optimize your rewards while you're doing that. So you're learning while you're optimizing, and so you care not only about what you learn in the end, but also what rewards you get during the decision-making process. And one of the class of problems that really this matters is problems like operations management problems, where the action you are taking in a reinforcement learning is really a decision you're making in the real world with actual implications on your revenue and your profits. So one typical example I like to consider is inventory management problem, where your states could be the state of inventory for different products, and actions are how much inventory you order. And then your state transition model is basically how the inventory transitions based on the demands that you get. And you don't know how world generates the demand, or you want to learn that. And these state transitions could be very complex depending on what kind of considerations you have, like product expiry, product consumption, other reasons of you can increase the product by ordering more. And rewards again could be generated from different sources. It could be positive if you satisfy some demand, you produce some sales profit, but it could also be negative if you have a lot of inventory in your inventory, and you could be paying holding costs for those inventories. So now here the problem of learning the demand distribution while maximizing revenue is very important, because every time you order the inventory, it actually costs you something. And if you don't sell enough, then you are losing the opportunity of selling while you are making these decisions. So let's now look at the abstract model that we are looking at here. So again, it's an MDP, like in a regular reinforcement learning problem. we are looking at an MDP where we know the state space and the action space, but we don't know the model, meaning that we don't know the state transition distributions, P here, and the reward distribution, so expected reward is R. So every time you take an action, AT in state ST, you observe a reward generated from this unknown distribution which depends on the state and the action, and you observe the transition to the next state based on the state and action you are in. Okay. So the solution concept is that you are looking for what policy to use, how to map a state into an action, and the goal is to maximize total reward over an horizon. So the total reward over an horizon captures the trade-off between the reward and learning that you are doing while you're making these decisions, because you can divide this horizon into, I want to spend this much time exploring different options, I want to spend this much time exploiting this option, but however you divide, you will be paying the total penalty, the total reward you will be gaining. Okay, so your goal is to learn this MDP from observations while maximizing the reward. And this kind of setup really highlights the problem of exploration versus exploitation. And to explain that problem, let me take an example of a single state MDP, and many of you are already aware of this, so you can snooze if you want. So the idea here is that if you have a single state MDP, and the only thing you don't know then is the reward distributions, because there is no state transition happening. So now that's simply called a multi-armed bandit problem. So here is an example. You have two actions, red and black, same transition probability is just 1 back to that same state, but the expected reward is higher for the black action. And here you can simply illustrate that if you just use an exploit-only policy, meaning like you did some maximum likelihood estimate or empirical reward estimate based on past observations, and use that to pick your action, then you could be stuck in the wrong action forever very easily. Because so here is a typical example given of sequence of rewards you might observe. There's a high chance that due to uncertainty in the rewards, you observed a low reward for black at some point, and at that point your empirical reward went down for black compared to the red's empirical reward. And from there on, because you will never play again the black action, you will never update its empirical reward, you will keep playing on the red action forever. So you can, with constant probability, get stuck in the wrong action forever. And this highlights the need for exploring. So basically what happened here is that we did not take into account the uncertainty in the black action. The fact that only 3 samples were available for black action. So we should have given some benefit of doubt to the black action, saying that we don't really know what the whether empirical reward is close to the actual reward or not. So we should give some benefit of doubt and explore the black action more. So how do we balance between that? Because we cannot explore arbitrarily, that would hurt in terms of revenue. So how do we balance between exploration and exploitation? Which means that, so exploitation simply means that we want to maximize the reward based on our observation. So that's the typical way to do that is to do some maximum likelihood estimate, like empirical reward maximizer. Exploration means that you want to take into account uncertainty in your estimates. So if some actions have less samples available, you want to explore them, you want to try them, even though they don't look immediately so good. And for this purpose, for the one state case, which is the multi-armed bandit case, there has been a lot of work on posterior sampling algorithms, also known as Thompson sampling, and I'll discuss this in more detail later, but for multi-armed bandit problem, the single state problem, we explained this quite well by now. The problem becomes even more complex when we come to real MDPs, meaning that multiple states. Okay, so here is a simple example. So let's say you have MDP with 2 states, S1 and S2, and now there is not just a reward but also a state transition probability. So now for simplicity, let's assume we know the rewards. Okay, so there is no problem of estimating rewards. The only thing we don't know is state transitions. So here again, in every state you have 2 actions, and I'm just writing them as red and black. In state 1, the action black gives you immediately low reward in both the cases, 0.6 and 0.4. The action red gives you reward 1. Immediately no reward. So black action gives you 0 reward, and state transition is 0.6, you remain with the same state, 0.4, you go to a different state. But in the next state, which only black action can take you here, you can actually take black action again and get $100. Okay? So now if you, suppose you played red action because immediate reward looks good, you will never be able to find out that black action could take you to this different state with $100 reward. But also, even if you explored a little and gave black action some chance, then only if you happen to take that other edge with 0.4 probability, you can go to the next state. And there, if you took the black action, then you can observe that $100 reward is possible. So you need to explore the entire sequence in order to find out that black action is good. You need to explore the entire sequence of transitioning to the next state, which only happens with 0.4 probability, and then taking black action again to see $100 rewards. So this is the problem in MDPs, that you don't need to just explore a given action in a given state. You need to be able to reach the state spaces that are important by your exploration. So you need to explore the sequences, the policies that that are good. So the problem is much more. So now if you do random exploration, in order to reach the right state, you might take exponential number of steps by random exploration. The states which are important, which can actually tell you which actions are good. So you cannot possibly do random exploration or greedy exploration at all. So now how do we do this in an intelligent way? And we come back to the posterior sampling idea, which is well understood in multi-armed bandits case. And the nice thing about this idea is that it's very simple and extendable. So let me explain it to you. So it's a very basic Bayesian posterior sampling idea. So whatever unknown parameters you have, so in multi-armed bandit case, the unknown parameters are, let's say, mean rewards for every action. In the MDP case, the unknown parameters mean rewards as well as transition probabilities, which you don't know. So whichever unknown parameters you have, you maintain, instead of maintaining an empirical estimates for them, you maintain a distributions over them, for each of them. Okay, so the way you maintain the distribution is, the distribution represents your uncertainty about your estimates. So you start with some prior over each of these parameters, and every time you make an observation, you update the prior to get a posterior by using just Bayesian rule. Okay, so Bayes rule will simply tell you that as you get more and more trials for any given parameter, more and more observations, the posterior will concentrate on true parameters. Okay, but the important part is that, so the mode of these posteriors, the modes will capture your maximum likelihood estimate. So you will be capturing maximum likelihood estimates through mode, but the important thing which captures exploration is the spread of these distributions. So instead of by maintaining the posterior instead of empirical estimates, you're also capturing the uncertainty through the spread of the posteriors. So less samples you see for any given parameter, like for blue here, you saw less samples. It will not only it will have more spread compared to red, for which you have seen more samples. So the spread will capture the uncertainty in the parameter. So in the first example where I said that the black action had only 3 samples, so the black action would have a very high spread, even if it will have low mode. So that captures the uncertainty. So now if you take a samples from these posteriors, then the blue curve, which has more spread even though it has low mode, will have a good chance to produce a sample from here instead of here. Okay, so it will have a good chance of getting attention because it will produce a high sample. So that will give it some benefit of doubt as compared to if you had used only empirical estimate. So to be more precise, the idea is that, So now how do we extend it to MDPs, right? So now in MDPs, to be more precise, you are trying to learn these unknown transition probability vectors. So you have effectively these S squared A parameters for every state and action. What is the probability of transition to the new state? Okay. So for each state and action, you maintain a probability distribution. Because in every state and action, when you take a given action, then you observe a sample of this probability vector. Okay? So whenever you observe this sample, you update the posterior for that parameter. To be more precise, here is the exact algorithm, how the exact algorithm will look like. And sorry, my Dirichlet is garbled here. So you maintain Dirichlet priors, which are a natural posterior to maintain for this purpose. You start with some Dirichlet prior on the probability vector. And you can just start with 1, 1, 1, 1 if you don't have any information. So you start with that prior, and when you observe a outcome, meaning that suppose you took action A in state S, then you will observe what state it transitioned to next. Then the posterior by Bayes' rule is simply the Dirichlet posterior with one parameter, whichever state you observed, let's say state I as the new state, that parameter increases by 1. That's all. So the posterior update is really simple in this case. And you can also see the intuition that how the posterior mean will concentrate on empirical mean, but the spread will be dependent on how many samples you have. So the posterior mean of the Dirichlet posterior is simply alpha I over the sum of alphas, which is basically empirical mean. Okay, because alpha I is the number of times you saw state I. And variance is simply, it's very, very close to 1 over number of trials of state S in action A. So as you'll have more and more samples of state S in action A, the posterior mean will concentrate with a small variance as well. So now what is the algorithm for our reinforcement learning problem? So now we show how we maintain a posterior distribution for every state in action. So how do we use it to actually make decisions? So we start with a very informative prior for every state in action. Let's say Dirichlet 1, 1, 1. And every round when we observe the new state, we update the posterior for only that state and that action. Okay, we don't touch other states and actions. Now when we have to decide what action to take, then we for every state in action, we take a sample of probability vectors, and that will give us a sample MDP. So sample MDP will be obtained replacing the probability model by our sample model. So here for simplicity, I'm assuming that you know the rewards. If you don't know the rewards, you have to do something like Multiarmed bandit for rewards posterior as well. Okay. So now you solve the sample MDP and compute the actions by using the optimal policy for the sample MDP. Okay, so that's your posterior sampling algorithm in a nutshell. What we prove theoretical results about is a little different from this algorithm. So we made some changes to allow analysis. So we made 2 changes. First, we don't do this posterior sampling and solving an MDP in every step. Instead, we do it only in epochs. So we proceed in something like doubling epochs. So every time some state in action has number of samples doubles, we change the epoch. So we have only logarithmic epochs. So in every beginning of every epoch, we generate samples and create a sample MDP and solve it. Then entire epoch, we use the optimal policy for the sample MDP. So that has in particular actually better for implementation because you don't have to solve an MDP in every step. You only solve it logarithmic number of times, but it also allows better analysis. We also made a change that instead of, in the beginning of every epoch, instead of sampling once from every posterior, we take S samples for every posterior. So that's why we call it optimistic posterior sampling, and we solve the best sample MDP that we get. In general, if you take S samples for every state in action, you have a lot of MDPs, possible MDPs, so you cannot enumerate them and find the best MDP, but there is a way to extend your MDP to solve it computationally easily. So now once we have the sample MDP, we use the compute the optimal policy, and then we use that policy throughout that epoch. Another change we do, the second change we do is that we add some initial exploration for the states in action with very small number of steps. We do a simple, very optimistic posterior sampling. And this is a very easy to sample distribution. Okay, so the summarization of results. So we show that the algorithm that I just explained based on posterior sampling produces a high probability worst case upper bound, which means that we don't. It doesn't depend on what prior you. It doesn't depend on how close your uniform prior is to actual prior. Okay, so you can start with just uniform non-informative prior, and we'll produce a bound on regret, meaning that we compare the rewards that we get, meaning our algorithm gets in t horizon, to the optimal reward, meaning by optimal I mean that if I knew the model, if I knew the true model, I could compute the best average reward policy. Okay, so if and let's say the gain of or average reward of the best average reward policy is lambda star, then I compare my rewards to t times lambda star. Okay, and for this regret definition, we show the precise result we show is that for any communicating MDP, and I'll explain what communicating means, with diameter d, we have that the regret is bounded by d square root SAT with for large t with high probability, and probability dependence on like 1 minus delta. For 1 minus delta, there will be a log 1 over delta here. Okay. So just to stare at this a little bit, it means that the regret increases as square root of t, but also increases at square root of SA, where S is the number of state and A is number of actions. So recall that the number of parameters, strictly speaking, was S squared A, but because for every time you play a state and action, you actually see the entire probability vector effectively. A sample for entire probability vector, not just one entry in that probability vector. The effective number of parameters is just SA, not S squared A. That's why you get this kind of result. Any questions so far? So just to compare with some existing works, so there has been a line of work on such worst case regret bound, mainly based on the UCB kind of analysis, and the best result known until recently was similar result for communicating MDPs, but with ds square root AT. And communicating MDP, I forgot about telling that. So communicating MDP mainly means that it is possible to reach from one state to another in that MDP. Okay, so if you are so this is kind of required because if you don't allow that, then you'll not be able to explore, because if you go to a state and it's not possible to reach another state from that state, then you'll be stuck in that state forever. So to allow exploration, it's kind of necessary that you have this kind of connectivity in the MDP. And communicating MDP is kind of the weakest concept, because it says that for every two states there exists some policy by which you can reach from S to S prime in expected time d. Okay? And you don't even need to know what policy allows that, and every pair could have a different policy that makes you travel from that state to another. Okay, so it's kind of the weakest connectivity concept. And the lower bound was also known for this problem, which was closer to what we prove is square root d SAT. So we still have a bound of square root d between the lower bound and S, but we close the bound on square root S. There's also been work in episodic settings. So in episodic settings, instead of communicating MDP, you kind of proceed in episodes, meaning you kind of break the MDP in every H step. So you restart after every H steps. So that kind of gives you already some kind of a bound on how far you can be by H. Okay, so in that case, both posterior sampling and optimistic like UCB bounds have been analyzed with similar bounds. So now I'll give some, how much time do I have? Sorry? 5 minutes? Okay. So I can give a brief overview of what kind of proof techniques we use. So to understand the proofs, let's just focus on an epoch, because that's the core part of the regret. So if you recall, the algorithm worked in epochs. In every beginning of every epoch, we sample an MDP from the posterior, and then we solve that MDP and use the optimal policy of the sample MDP for the rest of the epoch. Okay, so this happens in every epoch. So if we can bound and there are only logarithmic number of epochs, so if we can bound the regret in every epoch, we will be done. Okay, so let's bound the regret in every epoch. So what is the average regret in every epoch? So if you recall, for regret we compared t times lambda star minus the total reward. So the average regret is lambda star minus 1 over average, basically the average reward we get. Okay, so we have to bound that. So we break that into two parts. The first part is the difference between this optimal average reward, which we don't know. It is the unknown MDP's optimal average, and the sample MDP's optimal average reward. Okay, so this we can, this sample MDP we have it, and it's the optimal reward for that. Okay, for the sample MDP. And this is the difference between the optimal rewards of sample MDP and what we get. Okay, so if you look at this term here, these two terms are using the same policy. It's the optimal policy of the sample MDP. Okay, but this is the optimal. This is the reward of optimal policy of sample MDP on the sample MDP. Okay, whereas this is the reward we get when we use the optimal policy of sample MDP on the true MDP. Okay. Because we use that policy and actually apply it to the true world. That's the reward we get. So here, this would be really, really close, because this would just be some difference in asymptotic reward versus the actual reward if we were applying our policy to the sample MDP. But right now, there could be some gap here because this is on true MDP and this is on sample MDP. But still, it's about the difference between P and P tilde, right? The difference between the models. Okay, so this can be bound using concentration bounds. This is very different. This is basically not only the MDPs are different here, sample versus true, but the policies are also different. Right? This is the optimal policy of the true MDP. This is for the optimal policy of the sample MDP. So here both policy and the MDP is different. Okay? Here only, in the second term, only the MDPs are different, the policies are the same. Okay? So for this term we will use concentration bounds, but this one is more tricky. So here we will simply show that the sample MDP will have a higher reward than the true MDP because we took multiple samples and found the best of them. Okay? So we'll show optimism to bound the first term, and that's what I'll discuss a little bit briefly. So here, one of the key thing that we do is to relate the optimal, the gain, to the bias of the MDP. Okay, so this is the standard Bellman equation for average reward, and we want to relate the gain to the difference in model, right? To difference in P, because that's something we can bound. We know how much we changed P. And we want to know how that changed lambda, how that changed gain. So we come back to the Bellman equation and we say that this lambda is related to H, the bias. Okay? So the key result, and because I don't have a lot of time, go directly to that. So the key result is that your sample MDP will have a better gain if this inequality is true, if the model has a better projection on the true bias vector. Okay, so this actually makes it way more direct, this result. So it basically says that you can show that your sample MDP is optimistic as long as you can show that your model is optimistic, your sample model is optimistic with respect to only one projection to the true bias vector. A fixed, so true bias vector, the bias vector of the true MDP is a fixed vector. So you have to only prove about a projection on a fixed vector. Okay, so you can compare the two matrices by just proving something about two vectors by proving something about projection on a fixed vector. And now we can use the statistical techniques to say, okay, how does the projection, because that's now a number, okay, the projection on the true vector. So we use analysis of Dirichlet posterior, the anti-concentration or tail probabilities to show that the projection on H star is optimistic. Okay. And for the second part, as I said, this is just difference for the same policy between true MDP and sample MDP, and that we can bound using concentration bounds. Okay, so just to complete the presentation, one of the things that I'm very interested in working is more structured MDPs. So I like so this current result is very limited in the sense that it only works for finite state and action, depends on SNA. So it will be nice to extend it to continuous state and action space, especially continuous state space and large state space. But one of the interesting thing would be to look at more structured MDPs, like those that arise in inventory problems or other operations management problems like revenue management, because even though they are continuous, they have a lot of structure. For example, in MDP, you cannot have, for inventory problems, you cannot have arbitrary transitions, right? So you can only, if you see a demand and you can satisfy the demand when inventory levels are high, you can when inventory levels are low, then you can also satisfy them if inventory levels are high. So you have a lot of structure like that in inventory problems, and that can actually help a lot in terms of learning the models and so on. So that's something that I'm interested in. I'll take any questions that you have. Thank you. Yeah.
So I don't know much about reinforcement learning, but I was wondering whether this kind of approach has been used for real MCPs, or so far it's more like small state theoreticals.
So I think like the posterior sampling ideas have been used. I mean, Jan can tell more about in his talk as well. But I think the principle of posterior sampling has been utilized. It's definitely, I know of a lot of use cases in multi-armed bandits where people have used it, but they are starting to use it in reinforcement learning, the basic principle, but it's still a long way to go before we can have like a very solid implementations of exactly the posterior sampling ideas. I think right now it's used in conjunction with many different things. Yeah.
Yes, so one of the things that escaped me, I can't relate, sorry, but I mean, you have S squared A parameters and you can run this in square root of AS.
Yeah, so it's
like very key,
yeah, it is a key thing. Like it's one has to observe that even though there are S squared A parameters, when you take an action in a given state, you only observe the next state, right? So you only observe SA, S prime. But on these, at the other hand, you also see that you didn't go to other states. So you also observe like zeros for the others. So you effectively observe the entire vector, a sample for the entire vector. So if you think of for every SA, there is a probability vector, you effectively observe a whole sample as an unbiased sample from that vector. So even though there are S squared A parameter in the transition matrix, you are effectively observing a row every time. So that's why you can reduce the complexity. Yeah.
So one of the things, though, this pattern only kicks in after S5A.
Yeah, that's an important point. In fact, that was very annoying to us when we were proving this. For us, it happened because we had to do that initial exploration. Where is the bound? But I see that it happens in other results also. Where is it? Yeah, so I think in most worst case regret bound this happens because you don't have initial prior. So you kind of have to use this intuition that even though you start with very uninformative prior, if you go long enough, then your posterior will concentrate to the true. So I think if you have a good prior, this will probably not be necessary. So what happens, because you are starting with a very like uniform prior, so it can take a long time before it concentrates. So I believe like most worst case regret bounds have, I know that the two others have this.
I don't think the Jack's one, the one with the S outside, I think that it's any time. Okay.
Oh, the one with the D. Yeah, I know that all square root SAT bounds have it. Yeah. So yeah, I don't know. Maybe I don't know if it could be just a function of analysis. Yeah. Yeah.
It looks like the algorithm you have is something you can implement and actually run.
Yeah.
If you did empirically look at, does it seem to perform better?
Yeah, so we have looked at like, so we have implemented it for some like smaller MDPs, like finite state. Yeah, so it does look better in those, like the examples that other people have for difficult MDPs. So it does look better on those, but this has been done even Ian's work before on posterior sampling, that they they have also implemented it for some things. Yeah. So the better prior you have, obviously it will work better. Yeah. All right. Anything else? Thank you.